Hi, Dr. Kowalczyk. For my creative contribution number 2, I'm going to be working off of summative problem set number 5 and problem number 1, where we're looking at porphine with its heme group modeled as a particle on a ring, which we're saying has a diameter of 440 picometers with 22 electrons along the perimeter and coupled. So we're going to say M sub L is equal to 11. And the first part of the problem asks, what are the energy and angular momentum of one electron in the highest occupied energy level? So we're going to work with the equation E is equal to m sub L squared times h bar over 2 times the moment of inertia. And this comes from the Hamiltonian operator, where we're saying T hat plus V hat, which is the kinetic energy plus potential energy, is equal to the total energy. And as we've learned, we're going to set V hat, the potential energy, equal to 0, as we know that outside of the ring, potential energy goes to infinity. So now we have H hat is equal to T hat, which is equal to the kinetic energy, which we're going to set equal to the momentum operator squared divided by 2 times the mass, which turns into J squared, which is the angular momentum, divided by 2 times m times r squared, which with a little bit of math simplifies to this equation. And we're going to make a quick substitution of the inertia is equal to the mass of the electron times the radius squared of the ring. Using this, we're going to do a quick calculation, plugging in the known values to get 3.81 times 10 to the negative 18 joules. And that's for the energy. So for the angular momentum, we have a equation that's derived from a similar situation where we're taking the z component of the angular momentum, which is equal to negative I times h bar times the partial derivative in respect to psi times the wave function. So with a little bit more math, we get this simple looking equation here, which is 11, which is our m sub L times h bar, to give 1.16 times 10 to the negative 33 joule seconds for our angular momentum. So the next part, we calculate the frequency of radiation that induces a transition from highest and lowest unoccupied orbitals in porphine. So we know our transition is from level 11 to level 12, which would be lowest occupied to highest unoccupied. And we have delta E is equal to Planck constant times the frequency, which after a couple substitutions, we're going to take the difference in squares of the two energy levels and multiply that times h bar squared divided by 2 times the moment of inertia, make that same substitution as in part A, and we get this value here after we plugged in our known values. So we get delta E is equal to 7.23 times 10 to the negative 19 joules. We'll plug this value back into our equation and divide it by Planck's constant, which is equal, for a final answer, to 1.09 times 10 to the 12 hertz. So for a quick concept check to see why these equations work and why they're important, we're going to look at the following, in which the angular momentum is equal to the momentum times the radius. And according to Planck's hypothesis, momentum is equal to Planck constant divided by the wavelength, and that's multiplied times the radius. And we know that if a circle that a particle is traveling on has a circumference of L, in order for that particle to be stable, its wavelength must equal, lambda is equal to 2 pi r divided by n, and that's so that the wave matches up on itself. So once we plug in that term for lambda, we get the following, in which the radius term cancels out, and we get this quantized term here, in which we also make the substitution of n is equal to m sub L, which gives us this natural unit of angular momentum, which we see graphed in some of our lessons as a vector of j of z. So this m sub L can be substituted for the different energy levels. The greatest takeaway here is that angular momentum is quantized and is an integer multiple of h bar. So for the energy section, the Hamiltonian is only equal to the kinetic energy, as the potential energy is 0. And for this model, we say kinetic energy of a particle in a ring is equal to the momentum squared divided by 2 times the mass. And in this example here, we're not using the exactly correct operators for the system, but this will show what's happening. So we say momentum squared divided by 2m is equal to j squared over 2m times r squared. And that simplifies to j squared over 2i, which is just an easier way to write it. And here we can substitute in, based on the work we did up here, we can say that j squared on top is equal to m sub L squared times h bar squared over our 2mr squared, which gives us the full energy of the free rotor. So the relevance of this is that we can calculate and or approximate energy levels of an electron in planar pi conjugated systems. Examples of this are porphine, of course, which we just looked at, as well as benzene and others. And we can also approximate rotating diatomic molecules if vibration of the bonds is ignored. This can also help us approximate rotational energy levels if we're looking at molecules in rotational spectroscopy. So the biggest thing here is we study the quantization of angular momentum of electrons orbiting the nucleus in order to better understand its movement and interactions in the molecule.